Well, see, in the last lecture, we have developed the idea about enthalpy of solution and how it can be calculated on the basis of this enthalpy of formation of different ions if given, or ions or compounds. Like, so one homework I have given to you. Let's see how to proceed this. So everybody, first you have to. I think everybody have this question, so I'm directly coming to the answer. See, we have this equation. As per this equation, we have to find out the enthalpy change for this reaction, right? So since equation is given, so it is relatively easy for us. AgNO3 aqueous plus HCl aqueous gives AgCl solid precipitate plus HNO3 aqueous, right? So this equation we can visualize. What is the meaning of this aqueous? Aqueous means this is present in the excess of water. So this you can visualize like this: Ag plus aqueous plus NO3 minus aqueous, right? Plus this you can visualize like this: H plus aqueous plus Cl minus aqueous, and this you can visualize like this only: AgCl. There is no dissociation for this, and this HNO3 can be visualized like this: H plus aqueous plus NO3 minus aqueous, right? Clear? Okay. See, this is a ionic compound, so totally this will exist in this form. What we are assuming here, obviously this will be present in the ionic form, 100% ionic form, because this is present in large excess amount of water. Now you can write delta H naught of reaction is equal to 1. I'm taking first this AgCl, 1 mole multiplied by delta H naught formation of AgCl, right? Plus, I am taking H plus 1 mole multiplied by delta H naught formation of H plus aqueous plus NO3 1 mole and delta H naught formation of NO3 minus aqueous minus, right? Ag plus 1 mole delta H naught formation of Ag plus aqueous plus 1 mole delta H naught formation of NO3 minus aqueous plus 1 mole delta H naught formation of H plus aqueous plus 1 mole formation of Cl minus, right? So this is the net reaction. Now you can put the value. Now see, AgCl, it is given minus 127.068 minus 127.068, all have same unit, kilojoules per mole, and for this it is 0, and for this nitrate it is given, I think it is given minus 207.36, minus 2036, right? Minus Ag plus, what is given? Ag plus 105.579, 105.579. All the units are kilojoules, plus NO3 minus, NO3 minus is this, so this is plus minus 207.36 plus 0 plus Cl minus, minus 167.15, minus 167.159. So if you solve this equation, you will get minus 65.488 kilojoule, right? So in this reaction, this amount of energy, heat energy, will change, right? So on the basis of this delta H, formation of ions or molecules, whatsoever is given, you can calculate the delta H for any reaction. Now I am going to take up this bond energy, and this is the last topic of this thermochemistry, right? Well, now see this another term, bond enthalpy or bond energy. See, basically bond enthalpy or bond energy, these are the terms mainly used for this covalently bonded molecules, and bond energy data is always considered in gaseous state, because the formation and cleavage of bond always takes place in gaseous state. So suppose that if any molecule is given to you in the question in the solid or in the liquid state, so before using the data of bond energy, first you should convert that solid or liquid molecule into gaseous species, right? Gaseous molecule. So I am writing here first definition, what is this bond enthalpy or bond energy, and in that definition I will try to cover all those key words, right, or key points. Okay. See, bond enthalpy or bond energy, this you can define that the enthalpy of a reaction, the enthalpy of a reaction, enthalpy of a reaction resulting from the breaking of of a chemical bond uh, chemical bond in a gaseous molecule, in a gaseous molecule, right? In a gaseous molecule, to form the respective gaseous molecular fragment to form the gaseous, to form the respective, the respective gaseous fragment, right? Fragment is known as, fragment is known as bond enthalpy, or bond dissociation, enthalpy, because it is always true that delta H dissociation, this is greater than 0, that is positive, means endothermic, and dissociation of bond, right? And delta H association of bond, is less than 0, that is negative, means exothermic, right? So this is always true that in dissociation you have to supply the energy to the system, and in association there is a release of energy. This is always true. You may have some exception, like in the dissociation of ozone. So that is not the clear cut dissociation. There must be some secondary process is happening along with the dissociation. So otherwise this statement is clear cut always true, right? So if nothing is I mean no secondary process or no additional process is there, this statement is always true. Clear to all? Okay, good. Because sometimes you may find that the dissociation of ozone, that is positive, negative, or some other molecule, if it is given exothermic, that dissociation of this molecule is exothermic. So don't think that my this statement is wrong in that perspective. No, definitely if there is any violation of this, right, dissociation is given negative anywhere. I am not denying that negative is not possible, but if negative is given, means that is not the simple dissociation. That process is a complex process having some additional factor or additional involvement, or some secondary process is there. That is not the only dissociation process. Remember my these words, right? Otherwise this is always true. Okay, so bond dissociation energy and bond association energy magnitude is always equal. Suppose that AB is any covalent bond is given. So here the covalent bond is this AB. This is a covalent bond, and it is taken in the gaseous state. So bond dissociation energy is always equal to the bond association energy, but magnitude for this bond, right? For this bond means the amount of energy required to dissociate any bond, the same amount of energy release in the formation of that bond, or vice versa, right? And bond, and what is the meaning of bond energy? Suppose that somewhere it is given bond energy. So bond energy, it is default, it is always taken equal to the bond dissociation energy. Dissociation energy, right? It is default. So never consider bond energy as a bond association energy for any given bond, right? So for any given bond, don't consider bond energy as a bond association energy. You always consider bond dissociation energy until or unless it is not given. So if examiner has already given that okay, bond association energy is this, so you have to consider the bond association energy, that, right? One more thing here, that in case of diatomic molecule, where the simple molecules we have, like hydrogen molecule, suppose that if we take an example, so this HH bond is there. Suppose that in the gaseous state we have taken this molecule, although it is always exists in the gaseous state. So at any given temperature 1 bar and at any given temperature, if we specify 298 Kelvin or T Kelvin whatsoever. So if we take this hydrogen molecule and we convert this 2H gas, so gaseous molecule converted into corresponding gaseous atom. So this enthalpy of this reaction here, this is also known as enthalpy of atomization. Atomization. And you know this is equal to what, 435. I think this is the highest single bond energy, 435 kilojoules per mole. And this is the highest single bond energy between any atom in the whole periodic table. Remember this word, this is the highest value, 435. You don't have any single bond energy. I'm not talking about O double bond O or N double bond, N triple bond, and like that. No. If you compare single bond energy, so this is the highest energy in the whole periodic table, right? So this is also called enthalpy of atomization, right? So for diatomic molecule, it is okay. Diatomic molecule. So what is the bond energy of this HH bond? So here you can say bond energy of HH bond is here 435 kilojoules per mole. What is the meaning of this? The meaning of this is that if you want to cleave 1 mole, means Avogadro's number of such bonds, you have to put 435 kilojoule energy to the system. Clear? If you want to cleave Avogadro's number of such HH bonds in gaseous state at this specified, under this specified condition, you have to put 435 kilojoules energy, right? In other words, in the formation of Avogadro's number of such HH bonds in the given condition, this amount of energy is released from the system. Clear? So if you want to show this on the energy diagram or energy coordinate, so you can show this like this, that this is the energy coordinate. So H and H are here. So H2 is somehow here, right? H gas, and H2 gas under the similar condition. So see, this is the the difference of energy between these two. This difference is 435 kilojoules. It means our hydrogen molecule, it is more stable by 435 kilojoule energy compared to the constituent atoms. So this is the reason why atoms are unstable and molecules are what? Stable, right? So this is the method of visualization. In this way you can visualize these things, right? Okay. Now this is for diatomic molecule. Suppose that if we take some polyatomic molecule, then how to interpret this bond energy? So in case of polyatomic molecule, suppose that if we take water, example, if we take water, so gaseous water, H2O gaseous, in the first step, one bond will cleave and you will get OH gaseous plus H gaseous, and delta H1 here, delta H naught 1 is equal to 498 kilojoules per mole, right? And in the second step, this OH gas, this will go to the O gas plus H gas, and this time the delta H naught 2 is equal to 430 kilojoules per mole, right? So see here, in water two OH bonds are there, but we cannot say that the bond energy of both the bonds is equal, because in the dissociation of first bond this amount of energy is required, and in the second this. So how to report the OH bond energy? So if you want, you can see, you can add these two steps. So you will have this HOH gas gives 2H gas plus O gas. So delta H not total is equal to 498 plus 430 kilojoule, right? So in case of polyatomic molecules, there is one way to represent the bond enthalpy, that we can take the average. So basically here the bond enthalpy, delta H enthalpy, bond enthalpy, this is represented as an average of these two. So delta H not total divided by 2. So this is equal to 8 928 by 2, 2 4 is 8, 464 kilojoules per mole. So this is the average bond OH bond enthalpy is this, right? So in case of polyatomic molecule, we can what this express the bond energy as an average value, right? This is very simple, and this is called enthalpy of atomization here in polyatomic molecules. So this is called what? This total I mean energy required for this. This is 498. So 928 is the enthalpy of atomization for this, right? So if it is asked here, what is the enthalpy of atomization? So enthalpy of atomization is equal to this 498 plus 430. This is equal to 928 kilojoules per mole, correct? So both the data I have calculated here for this bond enthalpy. This atomization means the energy change in this reaction, complete 1 mole of that molecule converted into corresponding atoms. That is called enthalpy of atomization, right? Clear to everybody? Okay. So in case of polyatomic molecules, you can take this. Now see, if you want to calculate the enthalpy of any reaction with the help of bond energy data, then you can also calculate this. So enthalpy of any reaction, delta H naught is equal to sigma of Nj, J here product. Don't otherwise we should. J is the reactant, Nj bond energy, average bond energy of J plus sigma of product I, Ni bond energy of I. So you have to take the reactant minus product, reactant minus product. So by using this general equation, you can calculate the enthalpy of any reaction, right, in terms of bond energy. What are this bond energy? Bond and I represents here product, I product, J reactant, right? And bond energy, this is average bond enthalpy or average bond energy of the given bond. Average bond energy, bond energy of given bond, right? So now you can use this. Suppose that A2 gas plus 2B2 gas, it is given, and 2AB2 gas. Suppose that this reaction is given, all are in the gaseous state. So and if you want to calculate delta H of this reaction, so delta H of this reaction in terms of bond energy data, this is equal to 1 mole of this, so within bracket reactant minus product this time. Like calculation of enthalpy change when combustion data are given, then also the same thing, right? So 1 mole into bond energy of A bond, right, plus 2 mole into bond energy of B bond, bracket close, minus 2 moles into bond energy of AB bond. Bond energy of AB bond, right? So by using this general expression, you can calculate the enthalpy change in this reaction in terms of bond energy data. So if you have bond energy data for A2, for B2 and for AB, then you can calculate this delta H naught for this reaction. See, suppose that if in this reaction some component it is not given in the gaseous phase, then what you can do? Then first you have to convert that into the gaseous phase, and then you can calculate that in terms of bond energy. So some additional data is required to calculate delta H of that reaction, because whenever you are using the data for bond energy, you have to consider all the components, all the reactant and products in the gaseous phase, right? So I am giving you some data, bond energy data, just for your reference here, so that you can visualize that how this bond energy data you can use, right? So see, this is bond energy data for different bonds. See H, and now see CH bond 414, NH bond, this SH bond. Like if you see here, HH bond 435. So this is the highest bond energy for any homoatomic single bond. You don't have see here. Suppose that if you want to see CC bond, CC single bond, so CC single bond 331. If you want to NN single bond, so NN single bond 159, right? So if you go through this CL FF single bond, FF single bond 159, right? So this you just must go through this table and try to find out what different bond energies we have. Suppose that if you want to express the bond energy of FF, CL, BR, and II, halogens, right? So see FF, how to see this FF? F, and look here F 159, CL here, so this is 243, and BR here 192, and I here 151. So the bond energy is maximum. Bond energy is maximum for Cl2, then 243, after that 192 and 159, so Br2, and then F2, and then I2. So see here, see FF, CL, BR, II. So if you compare, see in the range of 200, 250, but HH 435. So Homonuclear diatomic molecules, the highest bond energy is for HH, not for any other, right? And you can see. So bond energy means if you want to cleave the chlorine, bromine, iodine, fluorine, so highest bond energy is required for chlorine and lowest for what? Iodine, right? So this is the bond energy data in kilojoules per mole, and here A, B, C, some references are there. So these references are mentioned here, that A is for C double bond O, like C double bond O, and it is also shown here. So you can go through this table, and definitely all of you should spend some time over the tables and their data, and definitely this will help you to understand the chemistry, right? Now, see, dear students, this is a very important question and very interesting question as well. See, predict the enthalpy of reaction for the oxidation of liquid methyl alcohol, right? Liquid methyl alcohol. And delta H naught vaporization is given for this. For water, it is given, and some bond energy data is given. So the question is actually mixed question. Means it is not simply you can use this equation, general equation, and find out what is the energy change here. You have to use bond energy, all these bond energy data only for gaseous reaction. So let's see how to solve this question, and this is definitely a very good question. So first of all, in any such type of question, you have to write the desired equation. So the desired reaction is CH3OH liquid plus O2 gas gives, because 1 bar pressure and 298 Kelvin. This is the standard condition what we are using. So this have to define first, and CO2 gas on the oxidation of this, and this H2O liquid. Keeping this 1 mole of this, you have to first balance this equation. So 2H2O, 2H2O, 3 and 1, 4, and 2 and 2, 4, 3 and 1, 4. So this is 3 by 2. So this is the balanced chemical equation. For this, it is given the task to calculate delta H, right? Clear, everybody? This is the desired reaction. So in any such type of question, you have to first write the desired equation. Now try to write all those equations of which information is given, so that you can algebraically manipulate all those equations and get the delta H for this reaction, right? Now I am writing the other equations. CH3OH liquid to CH3OH gas, and delta H vaporization is given, I think, for this, that is what, 37.99 kilojoules per mole. It is given, right? So we can say this is equation 1. Now H2O liquid to H2O gaseous. This is also delta H naught vaporization. This is given 44 kilojoules per mole. This is also given. But I am not going to write this is equation 2. See here in the right hand side we want liquid, so I am reversing this equation. So I am multiplying with 2. So this equation is I am reversing. So I am multiplying with 2. So we can write here H2O gas 2 gives 2 H2O liquid. Now this time delta H naught, this is vaporization for methyl alcohol, and this is delta H vaporization for water, and this is, now this is not vaporization, now this is delta H condensation. So this is equal to, no, we cannot write condensation because not in 1 mole, for this is for 2 mole, but okay, because I have multiplied with 2 as well, so I am simply writing the reaction. Delta H naught is equal to minus 44 into 2 kilojoules per mole. I am writing this is equation 2, right? So this data is given, but this data we are not going to use here in this, because here we want H2O liquid in the right hand side. So I have and 2 moles of water liquid are required, so I have multiplied this equation. So accordingly in delta H also multiply this 2 and reverse this equation. One more information is given, that the CS3OH gas plus 3 by 2 O2 gas gives CO2 gas plus H2O2 H2O gas. This is also, so I am writing this is equation 3, and delta H for this reaction we can calculate by using bond energy data. It is given but indirectly given, right? The value of this is given but it is indirectly given. So now you can calculate this reaction in terms of bond energy. So this is equal to CH3OH. So see, CH3OH structure is also important here. CH3OH. So in CH3OH, first I am writing reactant. So 3 moles of CH bond. So 3 into what is the bond energy of CH bond? See, CH bond 414. So 3 into 414. 3 into CH. 1 minute, I will write first formula, then value. Bond energy of CH bond, right? Plus 1 CO bond is here. 1 into bond energy of CO bond plus 1 OH bond is there. 1 into bond energy of OH bond plus 3 by 2 into bond energy of O double bond O. So this is the reactant. Bond energy, sigma of bond energy of reactant. This is sigma of bond energy of reactant, right? Minus C. Carbon dioxide, what is the structure? C double bond O double bond O. So you have to write 2 into bond energy of C double bond O plus structure of OH is this, and it is 2 moles. So total 4 OH bonds. So 4 into bond energy of OH bond, right? So now you can say this is the sigma of bond energy of product. So reactant minus product. Now you can put the value. So this is equal to 3 into bond energy of CH bond, which is 414. Unit is same for all, plus 1 into bond energy of CO bond, C single bond 326. 1 into 326 plus 1 into 4 OH bond, so 464 plus 3 by 2 into bond energy of O double bond O. O double bond O is 498 minus 2 into bond energy of C double bond O. So bond energy of C double bond O is 803 plus 4 into OH bond is 464. So if you solve this, so you will get minus 683 kilojoules, right? So delta H naught of this reaction is minus 683. Now you can apply the Hess law. If you see, if you add this equation 1, equation 2 and equation 3, so you will get the desired equation, right? So applying Hess law, equation 1 plus equation 2 plus equation 3 is equal to desired equation. So delta H not for 1, that is delta H vaporization, equation 1, 37.99, delta H vaporization of methyl alcohol plus 2 into delta H condensation for water plus this delta H naught of reaction what we have calculated. This is equal to the we can say this is 3. This is equal to the delta H naught of this desired equation. So this is equal to how much? 37.99 plus 2 into condensation is minus 44 plus delta H naught 3 is minus 683. This is equal to, this is the desired reaction. So if you solve this, so you will have the answer. This is equal to how much? 733 minus 733 kilojoules, right? So this is the answer. So see, this is very interesting question which involves the data, all kinds of data, means enthalpy data, bond energy data, and then we have to calculate the delta H for this reaction. So if the species were not given in the gaseous state, equation is not given in the gaseous state, and if it is desired to calculate the energy in that reaction, then you have to follow this step. First you have to calculate first you have to design the desired reaction, then write all those reactions of which data is given in the question, then you manipulate those equations algebraically and get the answer. This is the simple way to calculate the thermochemistry questions, right? So hopefully all of you are clear how to calculate the enthalpy of any reaction in terms of bond energy data, right? Now see one more question. This is a very important question as well. See, this is bond energy data is given here, and it is asked to calculate delta H combustion for benzene on the basis of this bond energy data. One more data is given here, that combustion of benzene minus 3225 kilojoules per mole, but this is experimental value. So leave this value. First you have to calculate by using this bond energy data, then we will make some conclusion on the basis of this. So first you have to make the combustion equation for this. Simple. So benzene, don't write C6H6, you should write the proper structure for benzene, because you are going to use the bond energy data. So there should be a clear-cut bonds, and representation of bonds should be there. Otherwise, it is difficult for you to visualize how many bonds are there, right? So this is the structure of benzene. I am writing the combustion of benzene. This is gaseous basically, and O double bond O, combustion, reaction with oxygen. This will give C double bond O double bond O, gas, plus HOH, gas. So first we have to balance this. So 6 hydrogen, so 6 carbon, so 6 CO2, and 3 H2O, and this is 15 by 2. This is 15 by 2, right? So this is gaseous, O2 gaseous, CO2 gaseous, and H2O gaseous. So this is the reaction. Now we can formulate the equation for delta H of this combustion. Combustion is equal to, see, how many C double bond C? We are doing reactant minus product. So first we are writing what? Reactant. So how many moles of C double bond C? 1, 2, 3. So 3 into bond energy of C double bond C plus 1, 2, and 3. 1, 2, and 3. So 3 into bond energy of C single bond C, right? Plus how many carbon hydrogen? 1, 2, 3, 4, 5, 6. 6 into bond energy of CH bond, right? Plus 15 by 2. Okay, 15 by 2 into bond energy of O double bond O. So this is the total bond energy of reactant, minus 6 of this and 6 of this. So you should write here 12 into bond energy of C double bond O, right? 6 this C double bond O, 6 this, and So total 12 carbon oxygen double bonds plus 6 into bond energy of OH bond, right? So this is the total bond energy of product. Now put the value here and solve this. So 3 into bond energy of C double bond C, C double bond C is 590, 3 into 590 plus 3 into bond energy of C single bond C, C single 331, 331 plus 6 into bond energy of CH, I think it is 441, 414, 414, okay, 414 plus 15 by 2 into bond energy of OO, O double bond O, 498 minus 12 into bond energy of C double bond O, C double bond O is 803 plus 6 into bond energy of OH, 464. 464. So if you solve this total, so you will get what? Minus 3438, minus 3438 kilojoule. So this is the delta H combustion. This is calculated value, calculated, right? This is calculated value. But delta H combustion for the same compound, which is experimental, is minus 32, which is given in the beginning of the question, 3225 kilojoules per mole. 3225 kilojoules per mole. This is experimental. Experimental. Right. See, so which value you are going to consider actual value, this or this? Obviously, the experimental value is true value. This is true value. It means this value, what we are calculating from this is not true value. So how it is possible? This value is corresponding to this structure of benzene, means we can say that this structure of benzene is not the real benzene molecule structure. If benzene molecule is real, then definitely the combustion, enthalpy of combustion should be this. So this data suggests that this is not the correct structure of benzene. Means what we are considering here, C double bond C and C single bond C, they are not actually in the real molecule. So this difference of this calculated and experimental value, this is referred as a resonance energy, right? And so this way you can calculate the resonance energy. So resonance energy is equal to delta H combustion calculated, no, experimental, minus delta H combustion calculated, right? So you can write here experimental value is minus 3225 minus minus 3438. So this is equal to 213 kilojoules per mole. So this is the resonance energy. So by this way you can calculate the resonance energy. So if it is asked somewhere that why this discrepancy is there in these two values, so your answer is that this is due to resonance, and this is not the exact model or real model of benzene. What we are drawing on the paper, that is not the real molecule. So this is confirmed and cross-checked by this experimental data and experimentation, and this helps us to consider the resonance in such type of molecules, right? So in this way you can calculate the resonance energy in terms of combustion data and bond energy, bond enthalpy data. Similarly, if in place of combustion, if heat of hydrogenation is given, then also we can calculate, right? In organic chemistry, I have already explained how to calculate resonance energy in terms of heat of hydrogenation. So there are two ways to calculate the resonance energy. One is if heat of hydrogenation is given, other one is if heat of combustion is given and bond energy data is given, right? So in this way you can calculate the resonance energy, right? Good.